it's important to understand how easily you can solve some circuits by a transformation. And in circuits 1, we may teach you to always solve parallel resistances, but sometimes it's much easier to solve a parallel conductance. It's always easier to solve a parallel conductance. And if it's a capacitance, then we might want to use an admittance. So for instance, in example 2.4, and I urge you to always look at examples, it says that using Y2 will be easier than using the complex impedance Z2. So that equals an admittance. And is that really true? You may be uncomfortable using admittances and conductances, but R2 and C2 are in parallel. Right? We've got these two elements. They're perfectly in parallel. We've got current splitting between them and then coming back out of it. So they're perfectly in parallel. And that's a situation where it's a nuisance to solve if you use an impedance. So Z2 is equal to R2 parallel with 1 over SC2, right? That's, we have a, that's the admittance, or the impedance is 1 over SC2. And that would be equal to 1 over R2 plus 1 over SC2. And that would be, we can do a little simplification easily, 1 over R2 plus SC2, right? Because this, we can just, okay, oh, sorry, I need to have one more 1 over, yeah. So we have 1 over SC2, right? Now that simplifies as SC2. But Y2 is equal to the inverse of Z2. And that's just 1 over R2 plus SC2. And that might actually be a lot easier for you to work that way. When we're dealing with impedances in parallel, we can just add them. But I'll talk about that a little bit more in a bit. But so now if we wanted a transfer function, V out of S as a function of V in of S, that was still a lousy V. We now have minus Z2 over Z1, or that's the quantity we need. But this would be the same as the inverse of 1 over Y2 over Z1. And that equals minus 1 over Y2 Z2. So this might be complicated, but this makes it really easy to substitute in and move, because we've just got that fraction up above, we just drop it in the bottom. And so then if we put in those values, we have R1 times 1 over R2 plus SC2, or 1 over R1 over R2 plus SC2 R1. And if we multiply through by R2 over R1 on top and bottom, we've got R2 over R1, R2 over R1 times R1 over R2 plus SC2 R1, and that equals minus R2 over R1 over 1 plus SC2 R2. And of course, if S equals 0, then that goes away, and we just have minus R2 over R1, which is the inverting configuration gain that we should expect. And if S is equal to infinity, then the gain is equal to 0, because this becomes huge, and that's just 0. So for a very low frequency DC, we just have the inverting configuration, and if it's a very high frequency, we have 0, and we also have a 3 dB down point, where S is equal to 1 over C2 R2. So then we have omega 3 dB is made a little mess there. Omega 3 dB is just 1 over R2 C2. So basically, what I'm trying to tell you is admittance or conductance is easier for parallel. If you don't believe me, if we have a resistor and we have a conductance, let's go to a page. We have resistance, and the equivalent conductance. It's the same symbol, right? But now we call that G. That's a conductance. If we think about that same circuit element, we can think about it as a conductance, or let me write it this way. We can think about it as a conductance or a resistance. And in series, we have R1 and R2, the equivalent resistance is equal to R1 so that's easy, right? And if we have conductances in series, it's a nuisance. We've got G1 and G2. Then we have to do this kind of parallel kind of thing, or this inverse things, 1 over G1 plus 1 over G2. The inverse of that would be 1 over R equivalent. And this would be the same as 1 over R1 plus 1 over R2, which would be 1 over R equivalent. So then R equivalent is R1 plus R2. That's hard, right? So if we've got series combination of resistances or conductances, we would rather use the resistance. But what if we've got parallel? So we've got R1 and R2, or we've got G2 and G1. Well, over here, 1 over equivalent resistance is 1 over R1 plus 1 over R2. And that's a hard, right? And then if over here, we've got the equivalent impedance or conductance is just G1 plus G2. That's easy, right? And then we could find 1 over R equivalent, which would be the same as G equivalent. And that would be 1 over R1 and 1 over R2. Plus 1 over R2. So that actually the inverse of G equivalent would be R equivalent, which would be 1 over R1 plus 1 over R2. And we've got all the same relationships. And the same thing happens for impedance, where Y, the admittance, is 1 over Z. When you see parallel circuits, it's often easier to use conductance and admittance, at least for equations. When you're putting in values, it may or may not be easier, but when you're working with equations, it's almost always easier to just go straight to the easy way to solve for parallel or series, depending on the combination that you have.